Hi everyone, welcome back to the channel. Today we are going to discuss a super important concept in digital electronics, that is gray code. So you might have heard of it before, but in this video we are breaking down the way that the simple, visual and easy to remember. We will understand what is gray code is and why it is used, how it works, and even look at how the convert between binary to gray and gray to binary as well. So get ready, because isn't theory, it's knowledge and power real world tech like error correction, encoders and digital circuits. Let's get started. The simple concept, that is what is meant by binary or gray to binary. So let's start with the binary code and as well as gray code. So let's see the difference between binary code and gray code. So if you observe the binary code, so according to the position and the weight we have to change the binary code, the digits. So but the gray code is non-weighted or unweighted, so it does not depends upon the weight. So gray code changes on the individual position or a single bit. So if you consider from change from 2 to 3, so it is only changing at the first position. It is changing from only 1 to 0. Remaining all positions are isn't changed, are same. So if you observe the from 14th or 15th position, so all the positions are same except the last position, that is 1 0 is changed. Likewise, if you take any two bits correspondingly or consecutively, only one bit is changed, so another bit will not be changed. But in normal binary digits it is not like that. So if you observe from 3 to 4, so 0 0 1 1, so again the consecutive one, that is 0 1 0 0, 3 bits are changed. So this is the difference between binary and gray code. Observe 3 and 4, those are 0 1 1 and 1 0 0, both are changing 3 bits. Like 0 is changing to 1, 1 is changing to 0 and 1 is changing to 0. So if you observe the same thing in gray code, it is only changing one digit, that is 0 to 1 at the second position. Let's see the second example also, that is 0 1 1 1, that is 7. So if you are going from 7 to 8, so it is changing at a time, all are changing, the 4 bits are changing. So 1 0 0, that is 8. So if you observe in gray code, only one digit is changing from that is first bit 0 to 1. Remaining all bits are intact. As we saw in the that 8421 BCD in the previous video, in the classification video. So if you don't know about weighted or unweighted codes, so you can check out in the description that I have given about classification, the previous video. So I said in the previous video only, that is gray code is unweighted code. So unweighted code means it does not depends on the weight. Weight means above that, as in the previous slide I have wrote 8421. So if you sum those, any of those two, we are going to get the decimal digit. So in the gray code we are not going to get sum. If you sum that, you are not going to get the decimal one. So it is as unweighted code. Reflecting means also the same thing. The unit distance code means it will only change if you take correspondingly or consecutively. So it will only change only one digit. So that is, we can say that reflecting. So 0 is reflecting as 1 and 1 is reflecting as 0. So that is to the next bit. So it is also known as reflecting binary code. Consecutively only one bit is changing, so it is also known as unit distance code. As compared to binary code, it is less error free, because it is minimum error code, because it is only changing a unit distance. It is from 0 to 1, 1 to 0, the consecutive bits. So it is a less error we can identify. So as well, whereas in binary code, in the normal code BCD, so at a time, suppose if we are going from 7 to 8, at a time 4 bits are changing. So it might give some errors in some of the applications, not all, some of the applications. Up to now we have saw the properties of gray code. So let's see the usage of gray code. So where we are going to use this gray code? So we are converting to gray code. So why we are converting? So these have some properties or some uses. So that is the reason we are converting into gray code. So the main use is we are going to use in the K maps. So used in K maps for minimization of Boolean expressions. or Boolean equations. So we are going to see in the upcoming videos what is meant by K-map and Boolean equations. So these are important concepts to minimize an equation. A big equation can be minimized. So let's see the second usage, that is gray code is used to reduce the switching operations. So as I said earlier, if we are going from 7 to 8, we have to switch 3 or 4. So from 7 to 8 it is 4. So that is 0 triple 1. So 8 is 1 triple 0. So we are going to switch at a time 4 bits. So that is more switching. So if you are observing gray code, we are going to switch only 1 bit, that is the last bit, that is first bit 0 to 1. So if you observe, it is less switching than compared to normal binary code. So that is known as switching operations is reduced. You can also clearly observe in this small example from 3 to 4 binary code and 3 to 4 in gray code as well. Up to now we have saw the properties and the usage of gray code. So let's now see the conversions. The conversion between binary to gray and gray to binary. So let's start with the binary to gray conversion. So in this example, let's take an example. So I have took an example like 10 1 0 1 0 in binary. So in binary, so that we have to convert to gray code. So let's see how to convert. So I have to there B3, B2, B1 and B0. So B3 is MSB, most significant bit, and B0 is LSB, least significant bit. So Z3 and Z0 also. So if you see the Z3 is equals to B3, that is MSB, that is same. So we have some formula, or we have some trick to not trick, we have some formula to convert. So the first G3 will be same as B3 only, that is 1. If we see the second bit, that is G2, so G2 can be obtained from the XOR operation of B3 and B2. So B3 is 1, B2 is 0. So if you XOR two different bits, so we are going to get 1. So if we XOR same bits, so we are going to get 0. So in this case we are going to get 1 because both are different bits, 0 and 1. The next bit can be obtained, like that is G1. G1 can be obtained by the XOR operation of B2 and B1. So that B2 is 0, B1 is 1. The XOR of two different bits is going to get 1. The last bit, that is G0, that is least significant bit, LSB, can be obtained by the XOR operation of B1 and B0, that is 1 and 0. So if you have XOR those two, we are going to get 1 because both are different bits. Let's see another example to get more clarification. So that is I am going to take 4, that is 0 1 0 0. So we are going to convert that as to prove also, that is 0 1 0 in gray code. So let's see, that is B3 is same as G3. So I am going to get directly 0 is obtained as 0 in G3. The second bit can be obtained by XOR operation of B3 and B2. So I am directly XORing. So both are different bits. So I am going to get 1. The next bit can be obtained by the XOR operation of B2 and B1. So both are different bits. So we are going to get 1. So the last bit can be obtained by the XOR operation of B1 and B0. So both are same bits. So we are going to get 0. Let's also see the conversion of from gray to binary as well. So I have selected a gray code, that is 1110. So in decimal, that is 11. So we are going to cross check or verify, that is 1011 in normal binary code as well. So the formula or conversion is, that is G3 is equals to B3, that is also same in the binary to gray code as well, in this gray to binary code as well. So the second binary bit, that is B2 can be obtained. So in this case we are not going to XOR Z2 and Z3. So it is not valid in this case. So we are going to XOR the previous bit B3, previous output B3 with the next input, that is G2. So we are going to XOR B3 and G2. So that is same bits. So you can observe B3 from above and we can observe Z2 from the above mentioned there. So both are 1. So we are going to obtain 0. The next bit can be obtained, like that is B1. B1 can be obtained by the XOR of So the previous output and the coming input, that is B2 XOR G1. So if you observe B2, that is 0. If you observe Z1, that is 1. So both are different bits, so we are going to get that is 1. The last bit, that is B0. B0 can be obtained by the XOR operation of the previous output and the coming input. So that is B1 and XOR of Z0. So if you observe B1, that is 1. So if you observe Z0, that is 0. So both are different, so we are going to get output as 1. So in this gray to binary code also, we are going to see the second example, so that you can able to understand or clarify your doubts. So you can see I have wrote G3, G2, G1, G0. So I have selected a number, that is 6. So that is 0 1 0 1. So you can convert from that is gray to binary. So the G3 is equals to B3, so I obtained 0 as 0 only. So here the next bit, that is G2, can be converted to B2. So the next bit B2 can be obtained with the XOR of the output, previous output and the coming input. So that is B3 and G2. So we are going to obtain that is 1, because both are different bits. So we are going to get output as 1. The next bit can be obtained, that is B1. B1 can be obtained by previous output XOR the coming input, that is 1 XOR 0, that is B2 XOR G1, that is 1 only output, that is B1 is 1. The final bit, that is B0. So B0 can be obtained with the XOR of B1, that is 1, and G0, that is 1. So both are same bits. So same bits XOR gives you 0. So that is 0. So you can also cross check. So that is I am taking 6, that is 0 1 0 1 in 6, that is a gray code. So if you observe in that binary code also, that is we are going to get 0 1 0 1 as output. So if you observe in the table also, so that is 0 1 1 0. So that is hence verified in with this conversion also. That formula is also hence verified. Thanks for watching up to now.